Hi students, we're going to talk a little bit about the first derivative test and what we can use it for. Basically, we can use calculus to help us sketch a graph, and that's where we're headed with this. Let's talk a little bit more in detail, though, what the first derivative test is. As you can see from our textbook, Business Calculus, here's the definition of the first derivative information that you get from taking the first derivative. So the function f is increasing on an interval from a to b if a is less than x sub 1, is less than x sub 2, is less than b, implies that f of x sub 1 is less than f of x sub 2. Let's draw a little sketch here so you can see what I'm talking about. Put a curve just like that there. So we have an interval from a to b. And then we have x sub 1 right there. And let's say we have x sub 2 right there. This would hold and would be consistent with what you see in the definition, that a is less than x sub 1, is less than x sub 2, is less than b. We're implying here that we are zeros right here and that we are on the positive side of the x-axis. So that way this is true. So what you see here then is you have x sub 1 and x sub 2. There are 2 points in between a and b, in between them. And if we go over to the y-axis, or our f of x, and this is x right here, we can see that f of x sub 1 is lower than f of x sub 2. Let me write that over here. F of x sub 1 is less than or lower than f of x sub 2, which is what our definition was saying. Let me erase now and talk about the other situation. What happens if a function is decreasing? All right, so let's make our function going in this direction. And again, let's go ahead and mark a and b. So a is where the function starts, b is where the function ends. x1 is smaller than x sub 2, and I'm going to bring x sub 1 up to the graph. So fix my axes over here a little bit. There we go. And x sub 2 will bring that up to the graph too. So we're still saying that x sub 1 is less than x sub 2, and both of them, those points are between a and b, those values of x. So now if we have a function that is a decreasing function, look what happens. Because we're coming down and x sub 1 is the smaller of the two values for x, when we go over to f of x, our y-axis, f of x sub 1 is higher than f of x sub 2. So again, in notation, f of x sub 1 is greater than f of x sub 2, defining what it means to be a decreasing function. So a little bit farther on in our textbook, let me make it a little bigger. So we have some information, interesting and good information we can get from the first derivative about the shape of a function. So it says for a function f, which is differentiable on an interval from a to b, like we had here, if f is increasing on a to b, then the first derivative, f prime of x, is greater than or equal to 0 for all x in the interval, the open interval from a to b. So if the function's increasing, the first derivative is positive, non-negative. And if it's decreasing, the first derivative is negative. F prime of x is less than or equal to 0 for all x in that open interval from a to b. And if the function's constant, the only place you would see that is if you had a peak or a valley where the derivative is equal to 0, right here and right here. We'll learn about when we use the second derivative test, or talk about that. We'll see how that could help us find and be able to sketch this curve by using that information. Let's come back to our function now. So we want to find the intervals on which this function, f of x is equal to 9x plus 4x to the minus 1. So what we want to do here is use our first derivative to help us figure out when this function is increasing or when it's decreasing. So let's go ahead and take the first derivative. So f prime of x is going to be the derivative of 9x will be 9, and the derivative of 4x to the minus 1 will be minus 4x. Remember, we subtract 1 from the exponent using the power rule, x to the minus 2. So that's our first derivative. What we want to do for that is figure out and find the critical numbers for this function. So what we're going to end up doing is making, let's try a different color. We're going to make a number line here. And it's going to help us determine the sign of our first derivative. Because remember, we were told that if f prime of x is positive, non-negative, it means that the function is increasing. If the first derivative, f prime of x, is less than or equal to 0, then it means the function is decreasing. And I know our textbook uses this notation of greater than or equal to or less than or equal to. I'm not so sure I believe that so much, because if f prime of x is equal to 0, then it means that the function is neither decreasing or increasing. We are at a peak or a valley. Because remember, what does that first derivative mean? It's the equation of the slope of the tangent line anywhere on the graph of f of x. So if that first derivative equals 0, it means we are at a peak or a valley. I'll leave these here to be consistent with our textbook, but technically, as I've seen it in other textbooks, that it's usually strictly greater than or strictly less than here. So what do we want to do to find these critical numbers? Well, we want to examine this function. Let's go ahead and rewrite it. So f prime of x is equal to 9 minus 4 divided by x squared. Okay, so we see a problem here. We can see that if I make a sign chart right here, I will have a problem at 0. And what I will do is above 0, I will put ND, not defined. We can't divide by 0, so that's going to be a problem for us. Finding the critical numbers next is what we want to do. And how do we find those? Well, we set the function equal to 0. We want to find the x values where those peaks and valleys are happening. So let's do the work over here. So f prime of x is equal to 0. So 0 equals 9 minus 4 divided by x squared. And then if I were to subtract 9 from both sides, I would have that negative 9 equals negative 4 divided by x squared. Divide out the negative sign from both sides and multiply both sides by x squared. 9x squared is equal to 4. Now let's see what's going to happen. Let me change color here. I'll have that x squared is equal to 4 over 9. And I want to calculate x. Remember, when we use the square root property, it's going to be the positive and the negative of 4/9 here, the positive square root and the negative square root of 4/9, which is going to be equal to, let me just put it over here, x is equal to 2 over 3, positive 2/3 and a negative 2/3. We have two critical numbers. So where this graph is reaching a peak or a valley is at these two values of x. So let me go ahead and put those, let me just for convenience start and put -1 and +1 on our number line here. And then let me mark our critical numbers. So 2/3 right here, the first derivative is equal to 0. And at -2/3, the first derivative is equal to 0. Okay. So now to continue, let me erase, and we need to find more values to check. We want to find regions where the function is increasing and where it is decreasing. So let me pause and I'll be back. Let's go ahead now that we found our critical numbers. Remember, they were at -2/3 and +2/3. Those are the x values where the graph is either reaching a peak, it's going to come up and down, or it's in a valley where it comes down and then comes back up. From this work, we can't tell which is which. We don't know if these are both peaks or valleys. We'll get a better feel for what the graph looks like, though, in a few minutes. So now what I want to do is I want to find what's going on in these 4 regions I've identified with the color pink. Is it increasing or is it decreasing? So I know at -2/3 the first derivative is equal to 0. Let's look at the left side of that. So -1 is a nice convenient number I can choose for x, and I can calculate f prime of -1, replacing my x value here in my first derivative. So 9 minus 4 divided by -1 squared, because our function or rule says it's 9 minus 4 over x squared. Well, -1 squared is +1. 4 divided by +1 is just 4. 9 minus 4 is equal to 5. What's the sign of this 5? It's greater than 0. I'm going to put a little plus next to that and call it the sign. So which means, I'm going to erase this now. Anywhere I am on the number line that's smaller than -1, including -1, because if I tried it for -2, -3, -4, notice as the numbers would get smaller, as x gets smaller from -1 all the way to -4, or so even further than that, this fraction is going to get smaller. We'll always have a positive result here, because 9 minus 4 over any of these x values is going to result in a positive number. So now we have something a little bit more complicated. We have to figure out between -2/3 and 0, a number we could put into our function. There's no whole numbers, or I should say integers here, that are just our whole integers, if you want to call them that. I'm going to choose negative 1/3. Now, why did I choose that? Because if this is negative 2/3, then it makes sense to me. Let's try negative 1/3, which would be right there. All right? And again, what am I looking for? I'm looking for what's going to be the sign of that first derivative. So I want f prime of negative 1/3, which is 9 minus 4 divided by negative 1/3 squared, or 9 minus 4 divided by positive 1/9. How do we divide fractions? We multiply the first fraction, which is 4/1, by the reciprocal of 1/9, which would be 9/1. So it would be 4 times 9 is 36. 9 minus 36, well, that is negative 27, negative, less than 0. Our sign is going to be negative right here. Hope you're getting the hang of this. Let's try it again, and I think you could guess what number I'm going to choose for this third region right here. That we want something between 0 and 2/3. Let's go ahead and choose 1/3. So positive 1/3 is going to give me the same result as negative 1/3, because I'm squaring. Doesn't matter if it's positive or negative, I'm still squaring that fraction. I'll always get a positive result. So we'll end up with negative 27 again, because it'll be 4 divided by 1/9, which is 9 minus 4 times 9, or 36, negative 27. Our third region here, it's negative. And then finally, the last region we want to check is the fourth one here on this right side. And what are we again looking for? A number we can use to test in each of these regions. Positive 1 is a good number here, because again, at 2/3, my first derivative was 0, meaning I reached a peak or a valley. So now, if I choose any positive number, I could test it. I like to use small numbers. They are very convenient to use because they are easy to calculate. So our first derivative evaluated at x equals 1 is 9 minus 4/1 squared, or 9 minus 4, or 5. And 5 is positive. We'll put a positive result here. All right, so now what do we have left? We have to find the intervals on which this function is increasing or decreasing. So you can see we have 4 areas here. So for the first one, and we can write it like this, that f prime of x is increasing on, let me get a different marker. So what's way over here on the left side? Negative infinity. And then it's increasing through negative 1 up to negative 2/3. I would also say there's another region on the very far right that at positive 1, it was a positive sign of the first derivative. But remember, there are numbers between 2/3 and 1 that we have to consider too. So we'll use an open interval starting at 2/3, which means it doesn't include 2/3. It just means anything bigger than that, all the way to positive infinity, would be increasing. And the last part, let me go ahead and erase this, so that way I can write the rest of our solution, because for these problems there will be 2 solutions: the regions where the function is decreasing, and the region or regions where the function is increasing. So we can now say that our first derivative, f prime of x, is decreasing on, now let's look at the regions here where the sign is negative. So you can see between negative 2/3 and 0, the sign is negative. So negative 2/3 to 0. Again, closed intervals because, open intervals, because negative 2/3, the derivative of the function evaluated for x equals negative 2/3 is 0. If x is 0, f prime of 0 doesn't exist. It's not defined. And on the other side, the right side, it would be the same thing, 0 to positive 2/3. We don't, by the way, use a union here, if you were thinking about that, because of the fact that they're a disjoint. We're just saying that there are two regions that this function is decreasing on. I should say the function, not the derivative. Let me remove those. And then there are two regions where the function is increasing. I hope this helped you. Bye, students.